Hey, so it's a pleasure to reintroduce Mohammed. So it's their talk on Floer Homotopy here.
Thank you. So as I said in the first lecture, there are several layers of complexity of trying to build up everything you know in homology, the world of generalized homology, and everything of Floer homology, the world of homology. And the first layer was just this counting question, just come up with an invariance, operation, come up with a theory. And that's what I talked about in the last two lectures. And then I said that the next level is to be able to build something like Floer homology. And that's more complicated because when you do come up with a theory, you already know what the homology of the space is, or its A-theory, its cobordism, whatever. It's already given to you. You just try to kind of find out from the space off. Whereas when you try Floer homology, the first thing you start with is, well, there's nothing to start with. You first have to construct the thing that has all the operations. So that's what I want to talk about. Talk about that. But not really kind of how to define the spectrum underlying generalized model. And this word spectra is somehow something familiar, should be familiar to people because if you don't like the word, you just imagine chain complex. You cannot define, don't usually define Floer homology without first defining the chain complex, which there's a differential. And if you try to do generalized homology, there is no natural chain complex to use. And the only thing we have is this notion from stable homotopy theory called spectra. So nonetheless, the way that I'm going to structure this talk is first I'm going to try to explain to you how the geometry that comes from moduli spaces, the theory of Floer theory, I say mostly the Floer theory, give rise to Floer homology groups without doing spectra. So this is like defining Floer homology and trying to do everything without passing through the chain. And it works well for cobordism. It's not clear yet how well it works for other theories. But when in the process of doing this, it will be clear that I'm not building all the structure that we need, and that all the structure that we need is, still missing. I assume many of you have heard, well, some of you have heard me give versions of this talk before, but I'm not going to worry about it. So, what is the starting point? The starting point is what is called the flow category. The term that was introduced by Floer and Seal. And what I want you to imagine based on the previous talks is that whatever I'm going to say right now, you can then replace manifold later by homofold or by derived homofold. And more importantly, you can then start assuming that you have some kind of additional structures, orientations, framings, stable complex structures, that will just make everything more messy. So what is a manifold flow category? Well, there's a set of objects. And in practice, this basically means either in Morse theory like critical points, that's a function, or maybe intersection points of the ground chains. Or maybe if you're doing one of these symplectic homology story, some kind of periodic orbits. And then you have morphisms between these objects, and there are many ways of arranging, kind of setting up the formalism. I'm going to set up the formalism in some way that's unfortunately a little bit not the simplest possible, but I feel like just to show a little bit of how we deal with difficulties. So I'm going to have my morphisms. Q, call it Q. This is going to be a manifold with locally constant function 0 infinity, and just to make my life simple. 0 infinity. Okay. And this function, we would call it the action, but I'm going to be lazy and call it the energy. And there's one more assumption that you have to impose, which is that this function is, in some kind of properness assumption that you have to be careful how you say it. It's proper, and there is no sequence going to the big sequence of elements which energy goes to. It's proper. And if you think that you're doing more theory than it turns out that you don't need the function. So in more theory. Function is just constant energy. Constant. And depending on how we set it up, you can basically think that it's given by Q minus F. But in Floer theory, this is the familiar thing where we have to measure the area of the homological curve. This is correction time. Now this is the category, so that's a familiar notion. So supposed to have a map. And sorry, this was going to be meant for the corner. We have a map like this. We have this energy map, so we can try to ask ourselves how are the two things compatible. And things just matter. And in most theory, this is the concatenation. What does that do? What does that do? And in Floer theory, we draw the exact same picture. Maybe you draw the cylinder. Okay, or maybe you draw it. The point to make is that in both cases, the energy function adds up, but also that when normally people they do it right now, and when people talk about it, but if you work in that far here, that is, this is the compact type moduli space. No, it's not compact, it's proper, so that's okay. Okay, and the structure is very pretty self-evident. And then there's like two more assumptions to impose. One is that So one, which is the fundamental one, which tells you that this map from here to here into the target, this is the inclusion of a boundary stratum, and all boundary strata are codimension one boundary strata. So we need that the composition maps define codimension one boundary strata, and all boundary strata. Yeah, all codimension one. And the other one, which is more technical condition, because I didn't say at the beginning that the set of objects was finite. The other one simply says that, if you give me that somehow this properness condition that I imposed here is not really the best properness condition, the better properness condition is to say that if you give me a P, then then there are finitely many Qs which receive a morphism from Q of bounded energy. That I mean, so kind of properness condition. The metapose here. So again, both of these conditions align naturally. So now the question is, what can we do from this data? What can we get from this data? And as I indicated in the first lecture, if you are doing ordinary homology, what you do from this data is you throw away almost all of it. You only remember the zero and one-dimensional moduli spaces, and then you say, the zero-dimensional moduli spaces define the differential, and the one-dimensional moduli spaces show that these squared equals zero, and now we're done. So, Cohn-Jones-Siegel point of view. So what they did is that they said, well, let's think first about the case where there's only 2 points. So if there are 2 points, 2 objects. And let's assume, moreover, that we're in some situation that this energy constant energy. Then we just have a single moduli space. Here, this is just a closed loop. And now, the important thing with this closed manifold is not its topology, but in the construction, but rather its vorticity. And we can think associated map from this n1 n2 on space and this construction is done basically by saying, I'll take this closed manifold, embed it inside n for n large, take the normal bundle, take the normal to neighborhood, normal bundle, and collapse Sn to the neighborhood, to come from the neighborhood, and then apply this classifying to make this map, which at every point takes the normal direction. Anyway, so these time spaces are the building block of what the homotopy theorists call an O, which is spectrum. And then what you can do is you can just say, this map gives me, by extension, so there's some number here n, which is not and it is not actually reflective of the dimension of the loop space. Okay. So you can turn this into a map as space map, and I'm just using some symbols here. And, and then from this, you can extract the homological by taking it. So this was just the case of two objects. Or for two objects, if you want to run through their machinery and if you want to extract the space that you care about, it doesn't if you care about it, goes to this machinery, you have to take an explosive manifold, you have to turn on this deformation, to turn on this punch rag and Tompkins stuff. And then have to deal with understanding with what spectra this is going to be a star, and then that's what you. But what I want to explain, that's with only two objects. And then what they did is basically work out how you do this with more than two objects. And what it means is that instead of having construction down from Sn to here, you have to have something which involves some kind of model manifold with corners mapping into here. And so there's some additional combinatorial complexity to it, and also the issue of kind of making sure that you can do the Conti-Agenton construction kind of put in. But what I want to explain is the way to not have to do any of this. Not have to do this Conti-Agenton construction. It takes a while to see what the benefit of that might be. But really the benefit of that is that it means that you can do all constructions at the level of geometry of the modular spaces. And then you don't appeal to this machinery unless you need to compute something. So this machinery is very useful for computing what is the Bordism group of a given space. You don't have to do that without using Conti-Agenton. But to build structure is actually extremely unpleasant to do. So the alternative approach is what I'm going to. The alternative approach is what I'm going to do is I'm going to define for you a notion of a Bordism group of a flow category. And that notion is going to be exactly, analogous to Bordism group of space. So there's going to be some generators. The generators are going to be some collections of manifold with corners, satisfying some structure, a little bit more complicated than it was in BC. And there's going to be some relations. So the generators are assignments so that will be P. So this is a manifold with corners for each P, which is an object of this category. And now here there's some choice. Again, this one that I picked, we have some energy map, and I can choose to define energy map. There's two settings. You can either assume that the energy map goes to R or goes to 0 infinity. I'm going to make it go all the way to R. That's kind of natural for some kind of application. Okay. And we need one more structure, which is that we need a map. From W, you need maps times this is exactly like the equation for having a module over a category. So I call these things Floer Homotopy. Not sure this stack the vector now. And I should have said here that this is properly locally constant and bounded. And this satisfies the obvious association. These are the generators, and the relations. Oh no, don't come up with that. Then you need some condition that's exactly like this condition, which says that if this was an manifold with corners, such that boundary of the P is exactly given by the union over all. Where here's the Q, P of the image of this thing. So oftentimes when I give this lecture, when I get talk about it, people ask me like, where would this come from? And it could come from many different constructions, but more theory, it comes from very natural thing to do, which is that you can take any manifold over your given manifold, which has a Morse function, and you can take fiber product of the descending manifold. Let's say that we have well, I don't want to too much conflicting notation. Let's just call it X for them. And X equals manifold. So say doing word that is Morse. Then it turns out that you can associate each critical point a manifold with corners. It's called P, just like that. And I'm using the same notation. It's almost the same. It's essentially the same thing. And what is it? This is flow lines with compactification. Space of flow lines that go from minus infinity from 0 to X with minus infinity going. But here's your frontier P. If you have a gradient flow line, and it cannot get the gradient is 0 here, it cannot approach here in finite time, but it can approach here in infinite time. And you can assume but these 2 points are very different. It's P, and this is the compactification, just to give you some idea, the compactification, what happens is that it has a sequence of this thing, and they, for example, sometimes they can break where into some flow line like this. Concatenation. So the curve basically spends most of its time over here between P and Q, and then finally goes to Q. And this is one that we'll study in manifold corners and everything. But this is not the full story that I wanted to tell. What I wanted to tell is that once you set it up, what you can then do is you can then assign each each manifold and over X. Like a flow model. By taking cross the X by the product of the basic problem. And of course, this is assume that you perturb them to make this fiber product. If we have some notion of borders in the group of flow categories, and it's a good notion, then it should have the property that in Morse theory it gives the right answer. So it better be that if we vary m by cobordism to m prime, that this equivalence class of this flow module doesn't change, and that motivates the definition of the relations. Flow models of borders exists. So let's call flow models 0, 1. There is W01. And now I have to say a few more words. So this is W01. This is an assignment of manifold with corners to which each is operated. Flow category 1. And now some structuring with same kind of structuring as we had here. Which we assume to be specific. I'm not going to write it. Okay. Now we also need to have that is W0. Inside W01. Inside W1. And now what we want is for these two structure maps to define all the boundaries. Okay. So that's the definition. That's the definition of a slur borders of a flow board of the flow borders. And again, I'm not going to do it, but I just want to say that if we had started with low category, when the manifolds were oriented, frame, or almost complex, or orbitals, or other orbitals, you can do exactly the same thing in that context. And in some sense, nothing changes. Just have to keep track of orientation. One thing you can do, one thing that I've done right now is that, because I'm working in the unoriented case, I don't even have to keep track of the degree of the generators. If you actually want to do anything about orientation, then you have to introduce some degrees. So now I want to this is very concrete definition. Okay. It's kind of hard to confuse, but you can show things like this has the this is some module over the order the name of the point. And its rank, to the extent that it's well defined, is bounded by the number of critical points. Those things are pretty easy to check. So there's two things many things are missing. There are two things that I want to talk about further. One is the way I describe it is that there's just a single, just have a single flow category in that problem. But if you want to talk about operations, if you want to have something going from some multiplication, goes from this Floer module to this Floer module to another Floer module, something like that, then you need to understand what, how are these flow categories related to each other rather than just have a single one. What can be assigned? Pair more generally. And two, how do we work in the chain law? So I will say a few words about the first part and then let's discuss it better. So for the first part, what you should have in mind is that this Bordism group that I just defined for you is a very, very special, it's a very special case. It's something that we should think of as a morphism from the point flow category to our flow category. And that more generally, flow categories form a category. So this represents some kind of philosophical shift from the approach of Cohen-Jones-Siegel. It also represents a shift from the way that we extract information from flow categories, from Floer theory to get Floer homology. Basically, what we say is when we do Floer homology, we say, take an almost complex structure, you determine some moduli spaces, then you just count those moduli spaces. Those counts define something, and you have the chain complexes, and then you just work with them. So, as I was indicating earlier, what Cohen-Jones-Siegel proposed to do is to say, well, take your Cauchy-Riemann equation, think of it as giving you all the moduli spaces, goes on the moduli spaces inside the flow category, and then use some Pontryagin construction to transfer from that to some category of spectra. And then that step, as I keep indicating, there's an enormous amount of value to be able to carry. Here, what I'm suggesting is, if you think correctly about flow categories, you can just stop there. That has all the structure that you know. And to clarify to indicate to you what I mean, in the case of frame Bordism, this is equivalent to the category structure. So nothing more is gained. Nothing is gained by trying to use Pontryagin construction, other than to try to compute something. But to compute something, you usually don't compute things in the chain up, you compute things on homology after having constructed what you have needed to construct. Okay. So in order to do this, in order to fully explain to you the category spectra, I have to look at the chain level, a bunch of things. But nonetheless, what I could do is try to describe to you some kind of something which is like what we call the homotopy categories. Just remember things like the homotopy, and that's what I want us to take people to that. And again, we're not doing spectra because it requires frame Bordism. Frame Bordism requires a notation, and I'm just doing something which is more and more. Okay, what is a morphism? Yes.
Like one of like the hard things with spectra is like finding like a nice model where you have like a symmetric noidal structure
Yes.
that do framed.
Yes. Yes. So look, so you can do whatever you want, whatever model you want. So the model that, so maybe this is, I should say that this is joint lumber. The model that we've settled on is to actually show that it is a quasi-category. Okay, and then you need to show that it is somehow symmetric in a quasi-category, whatever that means, and there seems to be a model that works quite well for this.
So that's like not a model category level. That's like considered it's only after.
You could do something more concrete if you really could, but probably we're not writing. First versions we had were much more. Yeah. But right now we decided that this is kind of the most natural thing, and I can say a few words as to why it's the most natural. Yeah. Okay. So I just want to point out that there is a distinguished flow category, and I already mentioned this. Which is just category with one object and no morphism. Technically, people don't like calling these categories. I just want to point out that there were no units. This was necessary because I had my maps already gone. Maps, the morphism spaces are mapping to 0, infinity, or interval. Any unit would have to go to 0. We don't want it anymore. It doesn't make a lot of sense. Okay, and then what I explained, it will be the case that that this thing which I call and multiple categories and bar, this is really morphisms. So I'm going to write and point. Bar, which is kind of morphisms. In our category. So that's then, if you understand, if you don't think about what you can possibly do, what's really happening here is that you can think of a module or an algebra as just being a bimodule. Bimodule on the left is the ground rate, which is what this point is, and on the right you have it. Square itself. That's all happening. So now we can just generalize morphisms that we really want them to be bimodule. Fine. So there are two flow categories. What is this? This is generated by fine. Okay. Manifold with corners. Great for the map, it's always to R. Constant property down below. Okay. For each pair. We define as an object and bar. Fine. And then there was instruction maps, and they're exactly like the instruction maps you had before, except that now there's two new ones. So there is W, so I can do it right. For E prime plus W prime. Right, there's a map we multiply on the left, and there's another map we multiply on the right. And just like before, these maps enumerate all the boundaries. It's not good. Codimension 1. Okay, so morphisms are flow by module, well, not exactly, they're equivalence class. And instead of, I'm going to assume you can just fill out what I said before, whatever I said before, there's some notion of morphism, flow module numbers equal. There's so the fundamental question is, if I'm telling you this story and I'm telling you that there's a morphism, well, first you could ask me, where did this come from? And it comes from the same thing. Again, in Morse theory, it comes very easily if you imagine that you have space. We'll take two manifolds, for example. If I give you space X, a manifold X, and a map from X to X prime, and I have a function F, and not a function prime. Then this induces, assuming this is generic, and if the map, let's call this map here, P is generic, we get such a thing. And you define it like as follows. Well, you take a critical point. Okay. And then what you do is you just flow along F. Okay. Until you get to some point. So this is exactly this kind of compactification, this much less descending manifold. So there's some little, this is the interior. Then you just apply phi. So you get down to some point, let's call this point down to 0. And then you apply phi. You have this point here, phi is down to 0. And then you just flow along gradient to that line to critical point. This is the definition of the flow by module associated to this map of topological space. In Floer theory, it's a little bit, in Floer theory, but actually when you see a picture like this, it tells you like you can do the same thing in Floer theory using Lagrangian codefont. I'm not going to. Same picture. Of course. You have something that's defined within, for example, you have orbit, then you have some morality here gamma, and this is a manifold, and this is a manifold and prime, and you can just relate the particular homologies by counting to the home of the curvature of the subject. That's like the structure as long as gamma is one is going to be found in the home. Okay, so there is a fundamental question which I have not addressed, which is what is composition? So you have now three of these. You have this flow module, they're going to need some names. I'm just going to use another letter. That's important. Now, yeah, no. Oh. Oh. Okay. And now we want to define something possible. And this turns out to be a little bit tricky, especially if you don't have familiarity with Floer theory. But on the other hand, if you just think purely algebraically, okay, what you would do is you would say, oh, well, okay, if I were imagining that these were these were algebras and these were bimodules, then I would define this composition as something like this, and define this joint union. And so we're going to evaluate this at this point. Do something like this. I would do take a morphism from here to here. I would tensor it with a morphism from here. I take an object here, I take a morphism from here to that object, and then I take a morphism to this object to here. Tensoring is basically just take the problem, and then I would identify things which are related by dimorphisms in here. And the teaching is for and the point is that this morphism can act on here. There's two maps. You can either multiply this by this to end up here, or you can multiply this by this. And then what you do is you would just take this tensor product, which is like tensor product over the ring modulo relation induced by the fact that we have this algebra. Well, this definition is a fine definition, and you can use it in the definition of a topological case. But why is this a manifold? This manifold movement. That's not fundamental question. It turns out it's not too difficult to see that it is a manifold. To see that it is a manifold. So the point is that when you try to do that identification, remember this arrow here, top one, is the inclusion of a boundary structure, codimensional boundary structure, and this map from here to here is the inclusion of a codimensional boundary structure. So that means that at a generic point, in an interior point, n or O, interior point of this product, you just don't see the equivalence relation because they're not equivalent. A generic point in this product is not equivalent to it's not touched by the equivalence relation. Not touched by this one. So, in fact, it turns out that that space is stratified to the quotient space. Stratified. Wait. So the top stratum is just going to be the disjoint union of the interior. And that this part clearly manifold. Then, for dimension 1 stratum, is going to be exactly what we put here. So what I mean by that, so it's going to look like this, and on this side you have zero. On the other side. And in the middle, you have exactly the thing that I drew. So this, I think of as something. Now I'm going to draw some pictures, which goes from P to prime 0, and this I think of as something which goes from. And in the middle, well, you do both. So here again, it's pretty clear. I think we all know that if you take two smooth manifolds with boundary, you move them together along the boundary, and you will get to a smooth manifold. You have to make some choices, and the usual statement here to make choices. So now the real question is what happens in the next movie. Could I mention 2 stratums? And I'm not going to keep writing all this stuff. I'm going to write it as I'm going to write. Here there's a quantity 0, here there's a quantity 1, then a quantity 2. And you should think of it that is where we stop. Okay. And over here, which is the interesting point, you now have something that stops at all points. Good. And so now the question is, why can you smooth this? Well, it's pretty clear locally you can smooth this, that once you start thinking about it, you're like, well, why does this have a smoothing which is consistent with whatever smoothing you built over the edges? And there are many, many ways to do it. But it turned out that, from my perspective, the easiest way to see that there is smoothing is to look at your infinity in this case, Q. And inside of this, you look at the subset where you satisfy this equation. And I'm going to write some number here, it's going to be 1/2. So what does this look like? It looks like, and then there's something which I don't know how to draw it, but so you have this entire case, and then you have some kind of upper below base, which looks like. Not the greatest picture in the world, but hopefully you can see that this is a region whose boundary is called this L, L2, and the boundary of L2 is actually R2, which is essentially the hyperboloid. The solution is 1, 2, 3 equals 1/2. This joint union, what we started, so the coordinate axis. So basically, if you want to convince yourself there's an easy way of smoothing this thing, there's almost no choices. All you do is you take this thing and you attach this, you attach it to this picture along the three faces, and what you see on the other side of it is something smooth. Now you're like, wait, what is that compatible with going from one boundary stratum to the other? Well, it's compatible with going from one boundary stratum to the other because if I were to take this picture and I set x1, for example, equal to 1. So here, let's actually cut so we set x1 equals 1. In the above picture, we have the inequality this 2 less than or equal to 1/2, which is exactly what you would do in the previous picture, when in the previous codimension, when you were trying to smooth that stratum. we get L1. So this is some obviously coherent family of pieces of manifolds with corners. So I call them Lego blocks because it's how imagining kind of things. And you can use them to attach. You have to make one additional choice, you have to make a choice of colors. So given a choice of colors, you take this thing which is singular, you attach these blocks, and suddenly you have something similar. So the last thing to say is that, even though this construction is pretty nice, it's clear that it's dependent on some kind of choice. And composite this. Now the question becomes, can we really, it's not hard to then show that this is associative at the level of Gordon class. But if you want to show that it's associative, on the nodes, you have to work really hard. The point is that it's kind of clear that what should really happen is that you should consider these broken, broken bimodules that stop somewhere, as themselves some kind of morphism. But it turns out because in the formalism of quasi-manifolds, what's natural to do is to say these are the modules are the edges of the simplicial set. The simplicial set has vertices given by flow categories. And then this kind of construction where you are building some one higher dimensional manifold to interpolate between this partition composition and the thing that you would like to call a composition, that higher dimensional manifold, that higher dimensional cobordism becomes exactly what you would call the two simples. And the two simples, but not use that to use this. Two simples is this. I'm going to stop in a few minutes. This is flow categorical, so I'm going to comment that. And I'm going to switch to now. 1, 2. Okay. And along this edge, you imagine having a flow module, and I'm going to again switch notation. Flow module. Along this edge, you have a flow module. And now you ask yourself, what would it mean to have something which fills the simplex? And the answer from the point of view of this perspective is that what you would have is like this, that you would have n bar 0, 1, 2. So this is an almost n bar 0, bar 2 module, but that lives over the interval. At one end, at 1, it's given by n bar 0, 2, which is this. Okay. And at 0, it's given basically by this formal composition that I did before. 1 posed over. So this is the natural place as far as I'm concerned right now. You can ask me, in a month whether I've changed my mind about how I want to formalize the story. The nice part of it is that this description that I gave you over here, how to see this corner, how to do it by attaching these pieces to this along the possible singular point. That is the proof that this inner form filling condition holds. Okay? The question is, when you do this kind of very abstract nonsense, very quantitative things, you end up saying, well, a quasi-category of the simplicial set satisfying the property. That property is basically that if I give you this edge, it can find two simplexes that fills it, and that's what that is. So I think I should stop here. Thank you very much.
So in your abstract, you said you'd tell us something about curvature.
Yes, I didn't have time. So the problem is curvature requires you to first understand how you handle this case. So I'll say one word, which is that I talked about flow categories. And there is some notion called flow multi-category. Okay. And the thing is, flow multi-category does not have a homotopy type associated to it. It's surprising because Lagrangian doesn't have a flow homological associated. But a flow multi-category has a category of modules associated. And that category of modules is vector, which if you want to say that. And that category of modules you should think of as the brain, the category of brains supported on your approach. That's 1 minute summary.
I have a question. When you had on the board on the right, you erased, you had something with like the first two steps of this Floer solution. What if you took the whole thing and tried to do it?
You really, so but I should have been a little bit more careful. So there's two ways to think about it. One way to think about it is you only look at P and Q, but you only look at your two objects. And in that case, actually, you need to put the whole bars. Okay. The other thing you can do is actually, later you will also realize that the other step is actually induced by the rest of the structure, very effectively trying to build an actual flow model. So these really, so it actually doesn't, in some sense, if you do it correctly, it doesn't change. That's one way to put it. But another way to say that is you probably should just write the whole.